Okay, let's take a look at Pythagoras' theorem. So before we get into Pythagoras, we just want to introduce a little about right angle triangles. So if we have a right angle triangle, meaning a triangle with a 90-degree angle in it, the angle opposite of the right angle is called the hypotenuse. Only the longest side of the triangle by definition, if it is a right angle triangle. The hypotenuse. Opposite of the 90-degree angle. So as you can see in the notes, even if you rotate the triangle around however you like it, the hypotenuse is always the opposite side. Extremely useful to put an arrow from the 90 across opposite to the angle so you don't get confused. So, identifying A, B, and C. So, C is always the hypotenuse. And A and B are the other sides. And the order at which we put them does not matter. C is always the hypotenuse, the longest side, opposite of the 90 degrees. And A and B, it doesn't matter. They could switch. I could put B up here, and I could put A down here. As long as C is the hypotenuse, it does not matter. So, a little bit of theory on Pythagoras' theorem. If we have a triangle, a right angle triangle with side lengths of 3, I'm going to put on the inside for this purpose, with a side length of 3 and 4, and we take the areas of those sides. If I draw a square off of both sides, well, if I draw a square, then this will also be 3, and this area will be 9. And if this is a square, this will also be 4, and this will be 16. And what Pythagoras figured out was that the area of the square coming off of the hypotenuse is the sum of the area of the two smaller squares. 9 plus 16 is 25. He knew that this area was 25. And the square root of 25 is 5. So the side length of this square is 5. That is Pythagoras' theorem. This square plus this square equals that square. A squared plus B squared equals C squared. Pythagoras' theorem, something we're going to be using many, many, many times. So, if I shrink this work up a tad, let's take a right angle triangle with those side lengths, but let's solve using the formula. So, if I take a right angle triangle with side lengths of 3 and 4, keep in mind not to scale, and I use Pythagoras' theorem. So, I'm going to write down the formula every single time I do Pythagoras' theorem. And I'm going to label the triangle A, B, and C. So, again, A and B don't matter, but C is always opposite of the right angle. So, A is 3. I can substitute into the formula 3 squared. B is 4. I can substitute into the formula equals C squared. Now, keep in mind, we're going to start doing more math on the left-hand side and the right-hand side. We don't cross sides unless we're doing algebra to both sides. 3 squared is 9. 4 squared is 16. And the right-hand side is still C squared. We haven't touched it yet. 9 plus 16 is 25. Now we're going to learn a new method, a method that we haven't seen before. 25 is equal to c squared. We're going to learn a method, square root both sides. So we're going to square root both sides. And we're also going to do stuff like mirroring. So I'm going to mirror it. The square root of c squared is simply c. And the square root of 25 is 5. And I'm going to circle my answer. And as you can see from the theory that we did above, the area of the smaller square plus the area of the other smaller square is equal to the area of the big square. So that was solving for the hypotenuse. Sometimes we have to solve for a different side. So let's take a look at another triangle. And again, these are not to scale. We have a right angle triangle. And I'm going to give a hypotenuse of 10 and a side length of 6. And I'm going to call this B. I could call it anything I wanted to, A or B. And then I'm going to label the triangle. A is the other side, and C is always the hypotenuse. So we're going to start off with Pythagoras' theorem again. A squared plus B squared equals C squared. And then I'm going to substitute into the formula. A is 6, so I'm going to substitute 6. I don't know what B is, so plus B squared equals C squared. C is 10. Now again, I'm going to do parts of things. 6 squared is 36. B squared, I don't have B information. And 10 squared is 100. Now, extremely similar to the last example. However, this time we're going to actually have to do algebra. So we're going to have to take the 36 from the left side and subtract 36 from both sides. Doing algebra, doing the same operation to both sides. We will see a lot more of this in equations if you want to go and get ahead. But if we have an equal sign, it's like a balance beam. If we take something off of one side, in order for it to balance, we have to take something off of the other. The reason why we do that is because 36 minus 36 is 0, so that's gone. And B squared will equal 100 minus 36 is 64. Again, we're going to do the same method as before on the last and square root both sides. And on the left-hand side, the square root of B squared is B. And on the right-hand side, the square root of 64, either on your calculator or doing prime factorization from the previous notes, is equal to 8. And we can circle our answer. I hope that you can see that, no problem. And keep in mind, in the notes, there are other ways of doing these things. You can manipulate the formula ahead of time. For example, C is equal to the square root of A squared plus B squared. C is equal to the square root of A squared plus B squared. Or, for example, B, or A for that matter, is equal to the square root of C squared minus A squared. We want to avoid these formulas until we're at higher levels of math. It's going to be a lot easier just to simply use Pythagoras' theorem. A squared plus B squared equals C squared. Just starting off with that formula and knowing how to square root both sides or how to subtract from both sides of the equation. Much simpler than learning two separate formulas. However, going to be extremely useful in the future once we have to do higher level math. Now, obviously, if you have a side length that is not an integer square root like 5 or 8, you're just going to get a decimal either on your calculator or by estimating square roots. Pythagoras' theorem, we're going to use this every single year up until calculus, carpentry, computer science, all over the place. Okay.